Hey, what's up, guys? So in this video, then I'm gonna to prove the cauchy-davenport. Okay. Cauchy-davenport. So previous, I already say what's this meaning, right? So theorem. So basically, if you take two subset of the Z mod PZ, and so this theorem tell you that the SUMSET is at least greater or equal to the minimum of P, whereas obviously the whole group is the whole group is the minimum the maximum you can get, right? So and A plus B minus 1. Okay, so obviously that P if you take a real number, then this proof is very trivial. But if you take the prime number, then the prime field is that it doesn't look so easy to prove why this is true. Okay, so right, so A plus B is basically a SUMSET. So it's A belongs to A, B belongs to B. Okay, so the proof the idea is we will use an induction on B, on sides of B. Okay. And notice that if B is 1, then this is true, right? So it's A plus B will be the same as size A. Okay. So this is a base case. So base case. And then also notice that if A is whole group, A is whole group, A is the whole group, then this is also true, right? So okay, so the only thing I need to worry about is that I can assume, right? So I can assume A is not a whole group. A is not a whole group, and size B. This theorem is true, right? Theorem is true for size B that's equal to maybe K. Okay, so I just consider A is not a whole group, and B is size K plus 1. Okay, so this is the induction step that I already finished. I assume this is true, and I want to prove that it is. I want to prove this case that cauchy-davenport is true. Okay, and now I define operator called shift. Right, shift is very simple, right? So if you take A plus B, or just A plus B, B belongs to B. Okay, so notice that if you shift A plus, if shift A or shift B will not change SUMSET. Okay, so so your A plus B is invariant under it's the same. It's the same under shift A or shift B. Okay, and so I can shift A and B wherever I want, and then I can prove this theorem. Okay, so the first thing I want to say is that I can since B is greater or equal to 2, right? B is 1, I already proved. So I can assume that I can assume B, and I can shift, right? I can shift B. So I can shift B such that B contains 0. So B contains 0 and some element G, where G is non-zero. Okay. Okay, so I can create G, and so now I have G 2G, 3G, 4G up to like P minus 1G. Okay, and so PG is 0 right here. So and also A is not a whole group, right? So notice A is not a whole group. A is not a whole group. A is not a whole group. So that means what? That means that A contains. So there is this let's say multiple everybody's X, right? There is a X belongs to 1 to P, such that X G belongs to A, and the X G of X plus 1 do not belongs to A. Okay. So you can see that maybe this is G in maybe G in A and 2G in A, and 3G in A, but 4G is not in A, right? Because obvious you can always find such pair, right? Because A is not a whole group, right? So it means that there is a X G where this guy belongs to A, but there is a X plus 1G where this guy do not belongs to A. Okay, so notice that in this case that we have using where P is prime, right? Otherwise that there will be middle 0. Okay. So I can shift A by this XG, right? So I can shift A by XG by shift to left, right? So that means that I can assume the following. I can assume that 0 contains A, and I can assume 0 belongs to A, but G do not belongs to A. Okay. The reason is that I know that XG belongs to A, and the X plus 1G do not belongs to A. Then I can shift left by minus this XG such that the 0 belongs to A and the G do not belongs to A. Okay. So notice that since I do this, then I know that 0 belongs to A and the 0 belongs to B, but G belongs to A, G do not belongs to A, but G belongs to B. This tells me that A intersection B is non-zero. Okay. And also it's less than, definitely different from B, right? Because B contains G, but A intersection do not contain G. Okay, so now we can finish the proof. Okay, so notice the following. If you do A intersection B plus as a subset plus a union B, you are less so will be subset of A plus B. Okay, and this proof is very simple, right? So imagine that imagine X belongs to A union B, but and X belongs to A, right? Obviously, that if you take Y belongs to A intersection B, that means that Y must belong to B, right? So you get A plus B. If X belongs to B, then the same. Okay, so this is trivial. So now A plus B subset will be greater or equal to A union B, sorry, A intersection B plus A union B. Okay, so now this is our new A prime. It's A prime. This is our B prime. Okay, so notice that B prime is less than sorry. This is okay, so A intersection B is less than B prime. Let's say maybe let's do this. Right, this is our new A, right? This is our new A. This is our new B, right? But now I can make an induction, right? I can make an induction because my assumption is that so A intersection B will be smaller, right? So my theorem start from I say that if B is less than K will be true, but now I'm working with original B has let's say K plus 1, right? But B is K plus 1, but now A intersection B is definitely less than K plus 1. Okay, so I can use my induction hypothesis on this guy, right? So I get minimum of P and A union B plus A intersection B minus 1. Okay, now this is simple, right? This guy will be A plus B. Okay. All right, so this is very simple discrete mathematics, right? A intersection B, a set of this plus A intersection B will be A plus B. Okay, so proof, finish. All right, so finally you get minimum of P. So this step is induction step. And then you get A plus B minus 1. Okay, so this is the proof of cauchy-davenport, right? So very simple. You do a shift. You first take the shift from B, and then you take some non-zero element G, and then you notice that there must be multiple G such that A belongs to and A do not belong, and you shift it, and then you do this A plus B. Okay, so let's finish the proof of cauchy-davenport, and the next video that I can give you the one very interesting application of this cauchy-davenport.